Picture a solitary piece of human engineering, a fragile machine constructed of aluminum and gold, drifting through absolute darkness long after the hands that built it have turned to dust. It carries the acoustic echoes of our oceans, the recorded greetings of our children, and the mathematical music of our greatest minds, perfectly preserved in the freezing vacuum. This is not a thought experiment or a science fiction concept. Right now, billions of miles away, the Voyager 1 spacecraft is living this reality, coasting into a deep time journey that stretches 1 million years into the unfathomable cosmic void. Launched when the space age was still young, Voyager 1 has long since completed its primary mission of photographing the gas giants of our solar system. Today, it is hurtling away from the Sun at roughly 38,000 miles per hour, piercing the interstellar medium where the solar wind gives way to the currents of the wider galaxy. However, the first major milestone in its million-year odyssey is one of absolute silence. In just a few short years, the spacecraft's decaying radioisotope thermoelectric generators will fail to produce enough heat and electricity to keep its delicate instruments alive. The faint, rhythmic pulses of telemetry that currently bridge the immense gap between the probe and the deep space network antennas on Earth will abruptly and permanently cease. Voyager 1 will officially transition from an active scientific observatory into a silent, derelict artifact, embarking on the rest of its journey completely blind and mute, entirely at the mercy of celestial mechanics and the gravitational tides of the Milky Way. Once the communications finally go dark, Voyager 1 will coast onward through a region of space still tethered to our Sun by an invisible gravitational thread, yet entirely removed from its warmth and solar wind. After about 3 centuries of completely silent flight, the derelict probe will encounter the inner edge of the Oort Cloud. This colossal spherical shell of icy debris is considered the true outer boundary of the solar system, composed of primordial cometary nuclei and frozen volatile compounds left over from the very formation of the planets over 4.6 billion years ago. Despite containing potentially trillions of icy bodies, the Oort Cloud is incredibly diffuse and sparsely populated. The spacecraft will not need to perform evasive maneuvers to dodge and weave through a chaotic, heavily crowded asteroid field. Instead, it will simply sail through an emptiness so profound that the nearest comet or frozen dwarf planet might be tens of millions of miles away from its specific flight path. Because of the sheer, incomprehensible physical scale of this cometary reservoir, it will take Voyager 1 nearly 30,000 years just to navigate through the immense dark thickness of this icy domain. Throughout this staggering period, the probe speed will remain relatively constant at about 38,000 miles per hour, coasting effortlessly on the residual momentum gathered from its initial launch and the massive gravitational assists it borrowed from Jupiter and Saturn decades ago. By the time it finally breaches the absolute outer edge of the Oort Cloud, the Sun will have faded into merely the brightest star in a dark, unfamiliar sky, its gravitational pull having weakened to a tenuous, almost negligible force. Freed from the Sun's dominant astronomical sphere of influence, the probe will officially sever its last physical ties to its origin, becoming an independent rogue traveler of the Milky Way galaxy. Around 40,000 years from now, Voyager 1 will experience its first notable stellar encounter in the vast interstellar expanse. It will drift within approximately 1.6 light-years of a red dwarf star known as Gliese 445, currently located in the constellation Camelopardalis. While a distance of 1.6 light-years, roughly 9 trillion miles, sounds overwhelmingly massive to everyday human comprehension, in the grand, sweeping scale of stellar astrophysics, it is considered a remarkably close shave. Gliese 445 is actually moving toward our solar system at a significantly high velocity, meaning the star and the inactive spacecraft are effectively rushing toward a distant, quiet intersection in the void. Yet, because of the immense distances involved and the vastness of the space between them, This flyby will not significantly alter the probe's trajectory or subject it to any intense gravitational capture that would pull it into a new orbit. Red dwarfs are incredibly dim, cool stars, meaning that even at its absolute closest approach, Voyager 1 would not be bathed in the intense ionizing radiation or brilliant visible light it experienced during its spectacular planetary flybys back in the 20th century. Instead, Gliese 445 will simply manifest as a transient, dull, reddish beacon in the endless night, slowly growing slightly brighter over millennia, before gradually receding back into the generic stellar background as the probe continues its relentless march outward into the galaxy. As the millennia turn into hundreds of thousands of years, the night sky surrounding the spacecraft will undergo a complete and radical transformation. The constellations, as we know them today from our vantage point on Earth, will warp, distort, and dissolve entirely. The stars in the Milky Way are not static. They are constantly in fluid motion, orbiting the galactic center at vastly different speeds, angles, and trajectories. The familiar, comforting shapes of Orion, the Big Dipper, and Cassiopeia will be unrecognizable, scattered by the relentless mechanics of deep time. Voyager 1 will continue to coast through this ever-shifting stellar landscape, encountering nothing but the incredibly sparse interstellar medium. This medium is a thin, near-vacuum soup consisting primarily of neutral hydrogen and ionized helium gas, mixed with incredibly sparse, trace amounts of microscopic dust grains forged in the death throes of ancient supernovas. Over the course of 1 million years, the gentle but constant bombardment by high-energy cosmic rays and these microscopic interstellar dust particles will begin to slowly, methodically erode the spacecraft's exterior surfaces. The multi-layered thermal blankets that once brilliantly protected its delicate electronics from the freezing cold of deep space will slowly degrade and peel away, and the resilient metal hull, including its iconic large, high-gain parabolic antenna, will become microscopically pitted and sandblasted by the friction of 1 million years of interstellar dust impacts. However, despite this slow surface erosion, the hard vacuum of deep space is an unparalleled, perfect preservative environment. Without atmospheric moisture, reactive oxygen, or destructive biological organisms to rust, corrode, and biologically decay its physical and chemical components, Voyager 1 will remain structurally intact for an incredibly long epoch. The onboard plutonium-238 within its radioisotope thermoelectric generators that once vibrantly powered its computers and instruments will have gone through thousands of radioactive half-lives, transmuting entirely into stable, non-radioactive isotopes, leaving the original power source completely cold, heavy, and inert. Yet the physical architecture of the probe, the struts, the sensory booms, and the golden record bolted securely to its main bus will stubbornly persist. The mathematical and astronomical probability of the spacecraft colliding with a main sequence star, a rogue exoplanet, or even a sizable interstellar asteroid over this entire million-year time frame is practically zero. Space is simply too vast, too expansive, and too profoundly empty to allow for accidental, random collisions between such relatively tiny objects. Instead of crashing dramatically or burning up in an alien planetary atmosphere, the probe is permanently destined to establish an incredibly long, sweeping orbital path around the supermassive center of the Milky Way galaxy. It takes our own sun roughly 230 million years to complete one single galactic orbit, slowly bobbing up and down through the dense galactic plane as it circles the bright core. Voyager 1, possessing its own unique escape velocity and outbound trajectory, will settle into a similar, immense, and independent galactic path. In exactly 1 million years, despite its staggering speed, it will have traveled roughly 50 light-years away from Earth. While this is an undeniably astonishing and record-breaking distance for any object ever created by human hands, it is barely a microscopic fraction of the 100,000 light-year total diameter of the Milky Way. It will remain firmly within our local galactic neighborhood, yet completely isolated. It will officially become a permanent, silent, artificial satellite of our home galaxy, bound forever by the collective gravitational pull of hundreds of billions of stars, vast invisible clouds of dark matter, and the incomprehensibly dense supermassive black hole anchored securely at the galactic core, continuing its solitary patrol long after the Earth itself has changed beyond recognition. Bolted securely to the spacecraft's chassis is a gold-plated copper phonograph record, engineered to survive over 1 billion years in the harsh interstellar environment. Even after 1 million years have passed, the electroplated grooves containing greetings in 55 languages, the mathematical equations of our fundamental physics, and the analog audio waves of human music will remain perfectly preserved. The physical probe itself will be a cold, lifeless husk, but this gleaming artifact ensures that our planetary legacy endures. Voyager 1 is our permanent signature in the cosmos, waiting patiently in the endless dark for a discovery that may never come.